Thank you very much again. And then we will move on to the second speaker, David Burkhoff. David was working on terahertz, is known for terahertz quantum cascade laser frequency combs, which he started during his PhD at MIT, and he's now assistant professor at the University of Notre Dame, where he's exploring the physics and the characterization techniques on the combs. Please, the floor is yours.
All right. Can you hear me and see my screen?
Yes. Yes.
All right, great. Thanks for the introduction. I'm really excited to be here today. IQCLSW was actually the very first conference that I went to. I went to the one in Florence in 2010. So I'm very happy to be giving a tutorial today. And so basically what I'm going to be discussing are recent advances in QCL comb physics and also characterization. But in general, I'm going to try to give a relatively broad overview of the field. So basically, what's a frequency comb? Well, we've already heard something about it. It's a light source whose lines are perfectly evenly spaced. There was some nice talks yesterday and today about this topic. And what that means is basically that not just that these lines are perfectly evenly spaced, but they're also completely phase correlated. And QCLs are a really nice platform for combs in the sense that because you can do band structure engineering, you can really make very broadband gain media that you can't have in other sorts of semiconductor lasers and in most laser systems, with the exception of possibly something like Ti-Sapphire. You can even get octave spanning gain media, which is what's shown here. And so kind of I'm not going to really discuss spectroscopy too much today. The main motivation for QCL combs is in the area of sensing. So in particular, dual comb spectroscopy, which is this technique that Holly had a nice talk about earlier this morning. And basically the idea is that you encode your optical spectrum features onto an electrical spectrum by having combs that are slightly differently spaced from each other. I'm not going to talk about this too much, but there's a new technique actually for anyone who does combs that we recently demonstrated, well, theoretically, and also it's currently under review, but experimentally. It's actually a radiometric technique. And so this is using two combs. You can actually mix them with a light source, which could be possibly broadband. It could be anything. It could be from space even, or remote. And by doing some math, you can actually recover the spectrum of that broadband source with both high resolution, so heterodyne level resolution, but also over the bandwidth of your entire comb. So you can have potentially ultra broadband heterodyne spectroscopy. So there's been a lot of nice work, especially done on the dual comb front, measuring in the mid-infrared, water, other gases at terahertz wavelengths. You can do, people have demonstrated hyperspectral imaging, which basically you use, what's nice about dual comb in this case is that you can basically acquire a spectrum at each pixel. And because the speed of dual comb spectroscopy is so fast, you can actually measure this in theory, you can measure this in close to real time, which would be much harder than with like TDS, for example. So what I would say the essence of a comb is, it is from the following diagram. So a perfect Fabry-Perot cavity or ring cavity is very comb-like, and of course what that means is that it has a uniform FSR. But this is only an ideal situation. In reality, no cavity is really truly a comb because of group velocity dispersion. And so basically your FSR becomes non-uniform. So kind of the general way to conceive of, I guess, all combs is that a comb is basically a device that uses nonlinearity to balance its dispersion, and it uses gain to balance its losses. So there's a nice drawing that Tobias Kippenberg made for this soliton paper of his. But I think you can really say this applies to all combs. And kind of traditionally, the big the big comb technologies, there's mode lock lasers has been around since the 80s. There, the gain is stimulated emission, and the nonlinearity is your gain modulation. Microlinear combs, of course, we just heard a lot about them. The gain there is parametric, and the nonlinearity is the Kerr nonlinearity, typically. And today I'm going to be discussing QCL combs, but more specifically FM-type QCL combs, so not mode-locked lasers, which are more difficult to make for various reasons. Where the gain is obviously, again, stimulated emission, but the nonlinearity is not, has not, I would say, not been quite as clear. It's been kind of assumed to be the Kerr nonlinearity, but a lot of recent work has shown that that may not be the case. So I'll discuss that. And so kind of my general outline of my talk, I'm going to be discussing all aspects of the combs, device aspects anyway. So generation, how do you make them? Characterization, how do you prove that you have a comb? Basically, what sort of measurements can you do? What should you do if you want to show that you have a comb? And then lastly, I'll talk about theory, which basically how can you describe comb formation, and really what I think is the so-called the essence of FM combs. And this is kind of a weird order, right? Because normally you would think, oh, why don't you talk about the theory first? But I think also this is more of a chronological order. So a lot of the generation work is from maybe about 5 years ago. The characterization is mostly from the last few years, and then theory is even more recent than that. And towards the end, I'm going to discuss this. What we're really excited about is this new analytical result that we think kind of pretty much explains almost everything that's been seen with all these FM combs, and kind of unites them into a coherent framework, which is something I think has been somewhat missing. So generation. So if combs are a balance between nonlinearity and dispersion, then of course the first thing you can do is you can think, okay, well maybe I'm going to do a lot of work to manage the dispersion and make that dispersion as small as possible, so your nonlinear mechanism, even if you don't fully understand it, can take over. And so historically, the first big result in this area was done by ETH and was in mid-infrared QCLs. And here they didn't do any particular dispersion engineering, but they did use a very broadband, heterogeneous, i.e. multi-stack gain medium. And they showed that, or they calculated that the GVD of this gain medium is quite low, at least within a certain range of the gain bandwidth. And they got this nice coherent looking spectrum. They did, of course, other coherence measurements as well, which I'll talk about in a bit. But they did see that they had this locking behavior. So some sort of optical nonlinearity overcomes residual GVD. They proved it with the beat node line width and beat node interferometry. And importantly, they showed that it was probably not mode locked. So it was more of an FM type comb. And this is something that's well known from quantum cascade lasers, because the gain recovery time of QCLs is known to be quite short. So it's hard to make them mode lock. So, if you want to, you can take this a step further. So if you want to do dispersion engineering of your combs and try to make that locking a little bit easier, you can think about ways of doing that. And dispersion compensation is, of course, something that's been done extensively within like the ultrafast community. And the idea is basically, if you have an optical system, you can calculate its GVD, which is first derivative of group delay, second derivative of phase, and in most materials, or lower frequencies are traveling faster than high frequencies. And so what that means is that a structure that delays low frequencies relative to high frequencies is going to compensate dispersion. So the terahertz range, you can do this pretty nicely with a so-called double chirp mirror. And what this is it's a chirped grading. And the grading is, so when I say chirped, what I mean is that its frequency changes, its period changes. And so longer wavelengths are going to reflect more from this end, whereas shorter wavelengths reflect from this end. And what that's going to do is it's going to compensate your dispersion. And so we did this to demonstrate terahertz combs. So here's an SEM. For this initial demonstration, we had used a homogeneous terahertz QCL. So this is actually a very high dispersion laser. It had 100,000 femtosecond squared per millimeter of dispersion. It did have a multi-peak gain medium, which creates some weird effects, and that's responsible for the shape of this spectrum. And of course, we did some various metrological tools to characterize the coherence, which I'll discuss in a bit. And then also the ETH group showed that you can get a comb regime from this very broadband gain medium that they demonstrated as well. So some other dispersion engineering techniques. There's been a lot that have been done in the last few years. I can't put all of them on here. So if you're not on here, I'm sorry. But I would say they fall into three major categories. You've got your double chirp mirrors, or DCMs, which is what I was just showing. This is very easy. This is relatively easy to do at terahertz wavelengths because, of course, the wavelength is so big, and so lithography is not so difficult. At mid-infrared, it's a little bit more challenging. So there's been a bit more work using gyratory interferometers, or GTIs. And the idea there is that you can have two reflectors, and they will, you can show that those two reflectors will act together to compensate dispersion. And this is kind of nice because you can actually use an external laser outside of your cavity in order to tune the GVD of the structure. Of course, these are all discrete compensators. You can also have more continuous compensators, which are coupled waveguide approaches. And so these compensate dispersion along the whole length of the waveguide instead of at the end, which is nice especially for a lot of reasons, actually. But the idea, most of what's been done here is you have two waveguide modes, and if you can rely on the anti-crossing between them in order to compensate GVD. So a lot of this is for explicit dispersion engineering. You can also take this a step further and do injection locking. So the idea is that this is not dispersion engineering per se. This is more akin to the gain or loss modulation that's associated with active mode locking. But it is a nonlinear process. So when you inject a strong modulation, that interacts with your field nonlinearly. And so the classic plot that you can make here is that if you have a beat note, and this beat note represents the beating between all the lines of your comb, so that would be this spacing here. When you inject too far off resonance, this beat note is basically unaffected by your RF injection. But as you tune the RF resonance into near this free-running beat note, you'll see that the beat note starts to get pulled in and then eventually locks towards it. And then it breaks off towards the other end. And so this is kind of nice because it's something you can do after your laser's already been made, right? And it can also potentially broaden the comb bandwidth, basically due to the fact that the gain of a QCL is a moderate function of bias. So if you in principle, if you apply a really large modulation, you can take advantage of that. Some other things that have been observed, I should mention harmonic states, which are states that are mostly investigated, I think, by the Capasso group. But basically, the idea here is that under certain conditions, you can actually get combs that skip multiple FSRs at a time. So instead of having a comb that is spaced by 7.7 gigahertz, you might have one that's spaced by some integer multiple of that repetition rate. So in this case, 400 gigahertz. They do tend to be a little bit more unstable than the so-called dense combs, but they have the advantage that they have more power per tooth, effectively, because the power is concentrated in a single line. So are these really? So that's kind of an overview of the types of measurements that have been done. I haven't discussed rings. Rings are kind of another topic as well, so I won't really get to that today. But if you want to characterize these things and figure out if these are really coherent, you also would want to figure out what these actually look like in the time domain. Are these pulses? Are they mode locked somehow? Are they FM? Most of these lasers are FM, but you want to be able to show that somehow. But first, we have to talk about the big one, which is, I think most people would agree, is by far the most convenient way of characterizing combs, which is the beat note. So the idea is that if you take a spectrum, maybe it's a comb, maybe it's not, and you shine it onto a detector, then if it's not a comb, there's an easy way to tell for sure that it's not a comb, which is that you'll get this beating between different pairs of lines appearing at different RF frequencies. And the result of that is usually that you get a really broad beat note, megahertz typically. But this is a really nice characterization technique, and people don't really discuss how great it is that often. So I'll bring it up because really what happens is you don't actually need a detector to do this. The self-detection of the gain medium is more than enough most of the time, and it's very sensitive and very fast, and so you can basically just read this off the bias wire. So you don't even need a detector. It is, for all intents and purposes, a purely electrical measurement. And of course, you can also sweep this as a function of bias to see where you have a comb. And so this is a kind of I call this a beat note map. Other people may have different names. Basically, what these beat note maps show is they show the current or voltage ranges over which you may have a comb. But this is again, this is basically an electrical measurement, so it's relatively easy to do. So of course, the question you can ask, and this was first investigated by the ETH group, is are all of the lines that you see in your FTIR spectrum really in your beat note? You can imagine that maybe only a couple are, and that the rest are hiding in the noise floor because they're so broad, right? You could have a sharp peak with 2 lines, and then maybe a bunch of lines which are so weak and broad that they're down here. And so they developed this technique called beat note interferometry, where you pass your source through an FTIR and measure the beat note through it. And so kind of the key features to look, the normal spectrum, of course, has a center burst at the FTIR zero path delay, whereas the beat note interferometry measurement does not. It has actually a dip. So if you Fourier transform these 2 spectra, what you find is that those 2 spectra, despite the fact that they're shaped very differently, are actually quite similar. And so that implies that things are coherent. So this was really the first, I think, really hard evidence that that there was really some sort of frequency modulated behavior going on in these structures, which are periodic in time, but not actually pulses. So a few years ago, I wanted to try to see if we could make this even more quantitative, and so we developed this technique called Swift spectroscopy or Swifts. And the motivation was if you look at the beat note interferometry, like what you're actually measuring, it turns out to be this expression. And I couldn't really make heads or tails of it. And then I really decided that most of the time what you want is in this expression in here, which is the inside of the magnitude squared. And so we developed a technique that allows you to do that. Measurement-wise, it's usually a bit different. So you actually demodulate your beat note instead of using an RF spectrometer. But this allows you to measure both the amplitude and the phase of your beat note, basically, with respect to some local oscillator. So whereas normal FTS is going to measure the power spectrum of your comb, when you Fourier transform this Swift's measurement, what you get is you actually get this weird correlation function, which represents the correlation of one frequency with its nearby neighbor relative to your LO frequency. So this is kind of nice for measuring coherence, but it also gives you some phase information because the phase of this number is actually the difference in the phase of nearby comb lines. And so kind of our initial motivation was to use this for coherence. And you can actually show that this is a way to measure first order coherence if you there's some caveats, which I'm not going to go into, but someone can ask me about if they're interested. And by dividing, basically the coherence function from Swifts and also the normal spectrum from the FTIR, you can actually figure out which lines are contributing to this beat note in a somewhat quantitative way. And so that's kind of what this is showing. Oh, am I muted? Okay, never mind. Yeah, I was muted for a second, sorry. So equivalently, you can show that this is actually related to the integrated phase noise of this beat pair. And what it is it's integrated over lab timescales. So you might be curious about how much phase noise you're measuring. You're measuring it from over minutes or even hour timescales, which depending on the length of your spectrum measurement. So this is really powerful, despite its relative simplicity. But of course, originally we developed this as a waveform coherence measurement, but we wanted to make, we eventually realized there was also a waveform inference measurement, or basically a pulse characterization technique. And so the idea is that if you have all these different phase differences, of course, what you can do is you can combine this information and take, cumulative sum these differences, and you can recover the initial phases up to some global factor. And from that, if you have no noise anyway, then you can reconstruct the electric field. Now, of course, this is actually why we bent over backwards to make this spell SWIFTs instead of just calling it heterodyne beat note interferometry like we originally did. And that's because pulse characterization measurements are typically animal named just by convention: frog, spider, etc. Of course, there's face as well, which we heard about yesterday, which is a really nice technique and is even more powerful. And an animal, swift is a bird, in case you're not familiar. Of course, this was very controversial in some circles. You should know this because of this classic result in ultrafast optics, which showed that if you're using linear optics and DC detectors, then it's not possible to measure the phase of an electric field. And all the ultrafast people remember this. But of course, they forget the second part of this, which is that you can actually, if you have AC detectors, you can recover phase information, which is actually in the same paper, but nobody remembers that. But anyway, this paper also actually theoretically discussed this possibility in the 90s. So the first measurements of direct invertible measurements of QCL comb profiles was done with terahertz QCL combs, the same one I showed before, and we got a result which was more or less in line with ETH and Jacob Kurgan's analysis, which showed that we had a frequency which was modulated in time periodically, but not pulses in the intensity. And in this case, you get a boxcar modulation, which is kind of interesting. And this is due to the line shape function. It's not a fundamental. It's not due to the dynamics of the laser. And surprisingly, why does this measurement work at all? Originally, we thought noise would probably kill it. Basically, the reason is that the measurement is basically that of phase difference, which is analogous to group delay. And group delay, of course, is a physical thing. And it turns out that for a lot of quantities related to the electric field, this is not useful for measuring the electric field itself, but it is useful for measuring delay-like things, such as intensity and frequency, where if you expand these out in terms of their coefficients, intensity and frequency both depend on phase differences of comb lines. And so you can, it's not a high temporal resolution measurement, but it's good enough for QCL type combs. And probably micro-Risier combs as well, although they typically have higher FSRs. So if we analyzed the noise and showed all these equations you can derive out of this. But kind of a big thing that you can take home from this is that if you're measuring a property like chirp, the chirp is going to be proportional to the square of your LO frequency, but also the cube of your bandwidth. So what this means is that it's really well suited for combs with gigahertz repetition rates, hundreds of lines. But for conventional femtosecond lasers, the noise is quite high because instead of having gigahertz rep rates, you have megahertz rep rates. You can still do it, and we did it just to show that it could be done effectively. But here we use a regular 80 femtosecond tie sapphire at 800 nanometers, so close to the visible range. And you can extract your spectrum, and you can do autocorrelation with this. What you'll notice is that even though it's an 80 femtosecond laser, it's been dispersed up to about 2.5 picoseconds because we passed it through about a meter of plastic. And that's because it's actually hard to find a range where both autocorrelation has high SNR and SWIFTs have high SNR. As you make your pulses really, really long, autocorrelation, your signal noise actually really goes through the floor, whereas SWIFTs actually stays the same. So that's kind of nice because it's a linear technique. But anyway, one quick thing I want to mention is that the envelopes of SWIFTs are actually, people who are doing this are often plotting the raw interferograms. I would not recommend doing that. I would recommend plotting the intensity and the frequency of these interferograms because these are hard to interpret, but the intensity and the frequency actually contain physical information. So for a pulse, for example, the slope at the origin indicates chirp on the frequency envelope. Same thing for an FM comb. The slope of the origin pretty much indicates your chirp. So it's recommended that you don't plot these instead, because they have much more information and you avoid the frequency domain altogether still. But anyway, so a lot of groups have been working on this, and a surprising result has been this linear chirp FM behavior. Starting with ETH, they showed that infrared QCLs can robustly produce not just FM, but linear FM. So here's some nice result from ETH showing this linear FM behavior. This is also seen in injection-locked IRQCLs from Vienna. And also it's been observed in non-QCL systems as well. ICLs, gallium and timonide quantum well lasers, quantum dot lasers, et cetera, et cetera, et cetera. So lots of different semiconductor lasers, lots of different types of technologies. And so it seems to be a pretty fundamental thing. And the general features is, of course, you have a linear intensity, a relatively constant intensity, but possibly with a dip or a jump at the point where the FM turns around. So here and here. And originally, I wasn't sure if these things were real, but actually, I've come to the conclusion that they really are. And you get a flat spectrum. And kind of what was surprising about this, and also made this somewhat controversial, is that this was not necessarily theoretically expected. So we want to explain this, and so that's why that's kind of the thing we want to keep in mind when we move on to talking about the theory behind these things. So this is really within the last 2 years, effectively, that this has been seen. So we want to see if there's a nice way of predicting the temporal behavior of these devices, and really a compact way of describing all of these phenomena that I just talked about. And so there is a way, and of course the best, most complete way is the Maxwell block equations, right? So the Maxwell block equations are basically a full description of the system. I don't think you need to use any, I don't think any GF is necessary for these systems, or it would be a little overkill for simulating these. But you model your electron populations and your coherences. You model your electric field, you use an envelope formalism typically, and you can integrate all these things numerically and you get really nice results. Or you can add other optical nonlinearities if you want to. And so all the Swift's types have been really reproduced with this formalism. So all of our earlier boxcar FM Swifts have been reproduced by Christian Juracek's group. This linear FM has been reproduced. These are time domain models. You can also do frequency domain models and reproduce these linear FMs. Again, you get relatively constant intensities, linear FMs for a lot of these things. And then for the terahertz multi-peak QCLs, you get this boxcar modulation, which is plotted a little bit differently here in case you're wondering why it doesn't look like a boxcar. So these are really nice, but in some sense, they're also kind of dissatisfying, right? Because you can do these simulations and the simulations look wonderful. But like, it can be hard to interpret why this is happening. And so there was some really nice work from Vienna last year, which showed that you could actually simplify, with some Taylor expansions, you could simplify the Maxwell block equations down to a master equation formalism, where, if you're not familiar with master equations, they're something that are commonly used in mode lock lasers. And you get all these different terms. In this case, you have terms from fields propagating in both directions, because we're assuming a Fabry-Perot cavity. So you have, this is a simplified version, but you have loss and dispersion, you have gain and gain curvature. I would say these are kind of like standardish terms that you see in mode lock lasers. But what's unique about this formalism, I think, is really this term here, which I refer to as the cross steepening term. That's something that I just made up. I'll explain why I call it that in a bit. But basically what it is a wave's conjugate. The derivative of its conjugate is affecting the counter-propagating wave. So you get this derivative of the E- field affects E+, basically. So this is kind of strange. But they had a lot of interesting results that I think kind of nailed the experiments, which was that they showed that zero dispersion is actually bad for comb formation. And basically that if you look at dispersion if you look at the coherence as a function of dispersion, around the GBD being close to zero is actually unlocked. If you want to have maximal bandwidth, you have to operate at like this point here, which is not too low. And I feel like this explained a lot, because especially the experimental data, especially in the terahertz, where the beat note is constantly blowing up and coming back together and so on and so forth. And they also showed that the Carr nonlinearity can shift this. And so this term that I think is important, I don't know, maybe, I don't know if they agree or not, but this is the term that generates most of the FM in this formalism. And they show, the reason I refer to it as a cross-steepening term is that it's very analogous to the self-steepening, which is usually discussed, which self-steepening, especially in fibers, is an intensity-dependent group velocity. So if you work this out, you get a bunch of terms which look like this. But what's different about this is that it's actually intensity-dependent group velocity, but propagating in the other direction. So so one field is affected by one field's group velocity is affected by the other field, going in the opposite direction. So we call this cross-steepening. But I think it's really the key at describing this formation, more so than other techniques. So we wanted to take this and go with this further. So now I'm talking about our recent coronavirus project, which is trying to get this sort of master equation formalism down. This needs to be numerically integrated, so it's it can be time consuming, and but we want to find one equation that describes this and also can be solved analytically. So can you do that? And so the inspiration, of course, is this Luggiato-Lafefe equation, which if you're not familiar, is very, very popular in the microresonator comb community. The papers which introduced it have been cited, I think, around 1,000 times together. And it was, these microresonator combs were first demonstrated in 2007, but it really wasn't until like 2013 that they were fully understood with the development of this sort of modeling. And what it is it is a mean field theory of propagation within a microresonator. And what we mean when we say mean field is that if the field does not change much within a round trip, then you can reproduce all these small time steps of your master equation with a single time step per round trip. So instead of taking, maybe a few thousand steps, you can take one big step of, one round trip or even multiple round trips. And, people have shown in the last few years that this produces a lot of interesting solutions. Not just solitons, but dark solitons, sinusoidal waves, I think time crystals, which I don't really fully understand most of these things. But these are all various interesting solutions to the LLE that have been discovered recently. And so we want to do that. But of course, there's a problem. This assumption, if the field does not change much within a round trip, it's actually horrible for Fabry-Perot QCLs. The changes within a round trip in a Fabry-Perot laser, especially one with moderate mirror losses, so this is especially true for mid-IR QCLs, maybe a little bit less so for terahertz, is that you have large internal gain, which balances your large mirror losses. So if you have, for example, a single-sided cavity, this is pretty high mirror losses, so we're assuming losses of 90%. And you just grind through the master equation solutions. This is what you get. So this is the intensity on the left and the phase on the right. And so what you see is that the phase actually is kind of constant. It's more or less, it's propagating in both directions, but it's not changing very much. Whereas the intensity is, of course, exponentially increasing, and then it exponentially increases more, and then it blows up, and then it drops down because it hit the facet, right? So this is not so surprising, but what it means is that the changes within the cavity are actually quite large. But actually the phase is, it produces this linear FM behavior. A parabolic phase means linear FM. So that's what you would hope to see, because that's what the data shows. But then, of course, if you actually look at what comes out of the laser, well, what comes out of the laser, if you look over long times, is very slowly varying. So this is the instantaneous frequency. But if you look over 5,000 round trips, now you'll look, you can't really see all the details here, so you can just look at the envelopes, which are the green and the red curves here. The changes are actually really, really slow over a round trip, whereas the changes within a round trip are really, really large. So this is very different from the case of a microresonator. So of course, these changes basically need to balance each other because it's a laser, and so the intracavity intensity fluctuations should basically be zero. There should be no net fluctuations above threshold, but you have to deal with this if you want to make a mean field theory. So, okay, we have this preprint where we explain all this. I'm not going to go into the math. I'm just going to throw up some pictures. But you have to you can do this, and then you have to take some steps. So what you do is you take this master equation formalism, you artificially double and extend your cavity so that basically your negative traveling wave is now propagating in the right direction. So now if you look at this intensity, just follow this little pulsation. The intensity is now constantly moving to the right, and then it resets over here. So now it has periodic boundary conditions. So this is something that's been done within the context of Fabry-Perot Caracombs, which is what this result was showing. But for lasers, you need to take this a step further. For lasers, you need to normalize this intensity to the steady state power profile of your laser, which is without any nonlinearities, which you can calculate very quickly. And so we had this K function, which basically represents the gain and losses that a laser sees inside the cavity. And so when you do that, so we define this F, which is basically the power normalized field. When you do that, the intensity now actually looks very constant. Of course, if you want to get back to physical intensity, you have to multiply by the K function. But now this thing looks like it is constant as it propagates through the cavity. And now you can average. So when you average, of course, if you average over a round trip, everything looks totally stationary. So this is nice because you can get basically a single equation. And the equation, I'm not going to show the whole thing, but this is the simplified version. It looks like this. So this is kind of the version of the LLE or a mean field theory that applies for Fabry-Perot QCLs, but also Fabry-Perot lasers, Fabry-Perot microresonators, so forth. And so it has the dispersion, it has gain curvature as before. You got this term, which is an amplitude restoration term, which causes your power to be clamped to a relatively constant value. And then you've got this crust steepening term. And you'll see that this K function did not go away. And in fact, this K function sticks around. It's extremely important. This K hat, by the way, is the convolution of K with what's inside. So it's not just around, it's being convolved with the field that we're trying to find, which is F. But this is nice because a convolution, of course, it's a circular convolution, and that's you can do that really easily with an FFT. And so with a split step method, I won't really go into, you can actually replicate the full master equation results with thousands times fewer time steps. So numerically, it's really nice in the sense that you can do it really fast, although it's probably it's basically as accurate as well, which I won't show here. But this formalism, you can extend it to include arbitrary line shapes, which is what we did here. So for the terahertz QCLs that I showed before, which had this multi-peak gain medium, you can reproduce this boxcar modulation that we saw in the Swifts for a mid-infrared QCL with a nicely shaped Lorentzian profile. You can get the linear chirp behavior. And then also, of course, you can simulate over really long time scales. You can simulate billions of round trips relatively quickly. And you can generate a beat node map, which actually looks a lot like what you see. This is for a mid-IR QCL anyway, where you have the single mode regime at low biases and FM comb at moderate biases, and then breathers and chaos at high biases.
You have two more minutes, David.
Okay, sure. So I want to discuss the analytical solution of FM combs, where you have to assume a few things, but you can do this. You have to assume no gain curvature, that your frequency is constant, or sorry, your amplitude is constant, and your K is approximately linear. And if you make those assumptions, you can actually grind this down to this result, which we're really excited about because it's very fundamental. And what it is it's kind of a new version of the nonlinear Schrodinger equation. So what you got is this dispersive term, which mimics a momentum in the Schrodinger equation. You have this nonlinear potential, which is now proportional to the phase, and you have something else keeping the amplitude constant. And by the way, this phase potential is generated by cross steepening. So if you compare this to the normal nonlinear Schrodinger equation, which you usually see in nonlinear optics, it's an amplitude dominant equation where you basically just have this amplitude term. And the solution of this is well known. It's a Seach, and you can analyze this. This FM comb NLSE is actually phase dominated, which means that its solution is totally different, but you can still find it analytically. And it turns out to be this FM comb shape. You know, you've got this parabola in space and then a carrier envelope offset as well. And so we're calling this a dispersive phase soliton. It's really a new type of soliton solution. It's kind of the opposite of an amplitude soliton. And so does it work? Yes, it does. If you compare this to the mean field theory as you initialize randomly, you could see that the soliton solution, which is shown in red here, is produced basically everywhere. So this is intensity, this is phase, this is frequency, and this is frequency domain. And you know, this solution is almost perfect, except at this point where the frequency turns around. So this point here, this is where the theory breaks down because of the discontinuity. So it's a little hard to analyze analytically, but we're working on that. In terms of physical parameters, this is really you can write down the chirp in very fundamental parameters. It's basically proportional to mirror losses, your small signal gain, inversely proportional to your GVD, and also a term from cross steepening. And you may freak out if you see this because this implies that a zero GVD has infinite comb bandwidth. But of course, this theory required that our gain curvature be small. And what happens is that if your gain curvature is too large, then this FM comb is going to start to exceed the gain bandwidth, which is going to prevent a stable comb from forming. So actually, even if your dispersion is 0, it's going to try to generate an infinite bandwidth FM comb. And of course, what ends up happening is that you lose your gain because of this your line shape, and your comb is no longer able to be stable. So this kind of explains the previous numerical results. So this is what it looks like if you have too little dispersion. It just kind of flops around a little bit and keeps trying to converge but doesn't. Of course, if you take this result and you initialize it periodically with a perfect cosine, then what you'll see is it actually converges to not the soliton state, but actually a different state where there are two jumps. So this is but with the same chirp. And so you can analyze this. You can imagine that this is a harmonic state. So I'm almost done. This is the last technical slide. But this theory explains not just solitons, but also harmonic states as well. And basically, all of these harmonic states are the higher order solitons of this NLSC, which is really nice. So because you have one equation to describe everything. So theoretically, the takeaways: mean field theory. It describes kind of all the QCLs, Faber-Perot's. It actually can describe rings as well if you modify it slightly. It's one equation to rule them all. So I would say the essence of FM comb formation is actually not the spatial Hilberting. I would say it's the cross steepening at the facet. I don't know if that's a controversial statement because that's where the phase potential comes from in your NLSC. Spatial Hilberting is there, but it mainly suppresses amplitude fluctuations as far as I can see. And then everything is described by this NLSC. Which describes pretty much almost all the FM comb features that have been observed as far as I can know. So in conclusion, QCL combs are an interesting platform for both local and remote sensing. You know, there's a lot of work that needs to be done at the device characterization and theoretical level. But, you know, and while not everything is understood, the community has really gone a long way of combing the desert and has come a long way towards understanding the interesting physics of these devices. So thank you all for your attention, and I'll take any questions.
Thank you very much for this presentation. I just scrolling through. Of course, I have questions.
Sure, yeah, I figured.
So, my question is regarding the split step method. Do you really think that this is faster than the model that we used?
Well, is it faster? I mean, so it's you certainly have to do less work to make it fast. You know, if you parallel, I know you did some tricks maybe involving GPUs in order to speed things up a bit, because I did the math and I think it ends up being almost as fast. I would say the real strength is probably more in the analytical abilities, right? So the fact that you can get this result.
Yes. Because
So yeah,
I
exactly.
agree.
Like
Yes,
taking an FFT is much slower than adding a bunch of times, right? So I don't know which is faster. I think you'd have to think a lot about the scalability.
yeah, of course, for analytic results, it's amazing. Of course, thank you very much for that. We of course we also wanted to do that.
Yeah. Well, I mean, like this, yeah, like we leaned pretty heavily on your results. So,
So, am I overseeing any further questions?
I would like to ask a question.
Please.
There is a question, yeah.
Much, David, for the very interesting talk. I think.
so sorry, I can't really hear you.
Very low.
Hear me better now?
Oh yeah, I can hear you now. Yeah.
Okay. Thank you for the talk. I think there's a lot to take in. So my question is not technical. I mean, I need to go back and see everything once again for that. I would like to ask you a comment. Do you think in this community needs a sort of unification of naming the things? I mean, you usually refer to mod-locked comms as to passively mod-locked pulsed comms, but QCLs are mod-locked.
So
comms. So
I'm going by the traditional meaning, I would say, of mode locking, which is pulses. So
okay.
I think if you talk to a random person at Clio, for example, if you say, I want to make a mode locked laser, I think they would say, you mean a pulse laser, right? So
yes.
Yeah, that's kind of the convention I'm using. I mean, you're right. Like, all of these things you can consider them mode locked, in the sense that they are phase locked and the modes are locked together. So like, I don't know. I'm just going by.
No. I'm just curious because I usually feel that I have a need for that. I mean, when I talk to people at Clio, that what's happened. I mean, I say, this is a comm, and they say, you have no pulses. It's not a comm. So that's the problem. I'm a metrologist. So for me, phase relation makes up a comm, not pulses.
Can I add one small comment for that? Actually, there is some literature from the 60s on FM comms. They produced it from using mostly active phase modulators, and there was no doubt that this was called mode locking. So
at some point, the meaning changed.
Yes. So in the end, I think there is a clear point that this can be called mode locking. And
no,
it should be generalized.
I like the name frequency modulated comms. I mean, clarifies a lot.
Jerome, you have a question?
Thanks, David, for this wonderful work. It's really, really encouraging. Also, really, very well. It's really great. I'm really enthusiastic about it. So what you showed is, of course, that there is what we were all kind of hoping for is a degree of universality in the solution of those QCLs. And I mean, from your work, can you sort of infer what are the ingredients that you need to make your laser follow that universality?
So basically, yeah, there's this result, right? Like, so what you really need, I would say, is so for this result, you can still see my screen. Yeah, okay. So for this result, you need to assume that your gain curvature is small. And I put that in quotes because we have not really we're working on this. We're trying to get an analytical solution similar to the other result. Right now, all we can say is that, this needs to be much smaller than your gain bandwidth somehow, right? And then also, of course, this is proportional, and gain curvature also is going to reduce this somewhat if you plug it in. So basically you need, another way of saying that your gain curvature is small is that you need really broad line widths, right? But it actually does not, I think there's a lot of room that can and needs to be done in terms of curvature management in addition to dispersion management, right? So taking your Lorentzian profile and adding some frequency dependent loss, which has the same shape, and then trying to flatten it out. Because in some sense, the problem is that you have too much gain in the middle and not enough gain at the edges, right? And so if you really want to make this effect dominate, then that needs to be the case. And then of course the other, you also need large mirror losses, right? Like that's the other thing that appears here. From this analysis, like I said, I don't think it's the spatial hole burning per se. I mean, spatial hole burning is there for sure, but like like the way to think about it is that you hit this facet, and the wave that's reflected is now seeing the incident wave, and it's modulating it, and there's a big difference between those things. So the wave is always seeing a much bigger version of itself, and so that's what causes this phase to grow exponentially. And so it's part of the reason I think why you would never really see this effect in like a microresonator comb, for example, right? Because in a microresonator comb, the losses need to be low, right? Like if your coupling is too high, then your Qs kind of start to really fall. I mean, you can only see this in basically like lasers where you have the ability to balance all those losses with gain.
Sorry, in this expression, you do not have any line width enhancement factor.
We do not know.
Right. And
sorry, go on.
So in your thinking, the self-consistency of the RF, if you want, that you generate, which you could also think of it as kind of being a phase modulation that you impose. If you have a diagonal transition, as you know very well, the internal field changes, you actually shift your gain and you add another term, which would be kind of a self-consistent. I mean, you can probably write it as a line width enhancment factor. But
we've not analyzed that.
Yeah. Right. Mm-hmm.
Interesting. But yeah, that's interesting. Like for this, currently in this model, the second you add almost anything else, it kind of becomes difficult to analyze, right? Like, yeah. I mean, to be honest, like the fact that this is actually an exact solution to that is kind of hard to make happen, because I mean, maybe we need to collaborate with like fluid dynamics people, because they know this stuff really well.
Yes, I mean,
but like for this, we're just guessing solutions and making the solution look right until we do this, because nonlinear problems are hard to solve, right? So like we don't have a solution where you added back in gain curvature, for example, which is
thanks.
The other aspect.
It's beautiful.
Yeah.
So I think we should move to the poster session soon. So thank you again, Burko, for this very nice and talk and very good explanation, I think, of the entire topic and introduction. It was really a tutorial-like talk, in my opinion. Very, very good.
Thank you.
Also thanks to all the other speakers of today, and let us meet at the poster session.